cloud. Okay, wonderful. Thank you everyone for being here. Thank you to our speaker today. We're really excited to start our third colloquium of this semester. Today we have our own Clara Sousa-Silva, and we were just laughing before the call about how strange it is to all be collectively, at the CfA, but most of us aren't spending much time there these days.
No time at all.
Right, exactly. And so anyway, Clara is a 51 Peg B fellow at the CfA. Previously, she spent time at MIT, and before that did her PhD in sort of the intersection of chemistry and astrophysics at UCL in London. So we're delighted to get to hear from Clara today, and I think many of us are going to learn a lot. And then we have about half of our time today for discussion. So if at any point as we go you have questions, if you could please private message me, Morgan, a few words about the topic of your question, so it doesn't have to be the entirety of your question, but just a few words, then I'll sort of start a running queue, and I'll call on you to flesh out your question, and we can have a conversation from there. So I think that is all of the logistics. So without further ado, we're delighted to have you today.
Thank you, Morgan. Okay, let's try this a third time. Can you see my title screen? Can you see only my title screen?
We see the presenter screen.
Okay, what about now?
It's frozen for me.
Okay, let's try a fourth time. Can you see the title screen?
No, we see the presenter screen.
What about now?
Yes, now we see it.
Okay, we're in.
Exactly, thank you.
All right, hi everyone. Thank you for being here. All that Morgan said was true. So I'll talk a little bit about my work, which all of it, no matter how kind of weird or normal, revolves around molecular spectroscopy. And specifically, I look at mostly extremely respectful and fundamental research, but it does have kind of endless applications, some of which are less respectful, like my favorite, which is looking for alien life. So I'll try to touch on all those aspects here today. So I sometimes like to reverse my work and imagine what it would be like to be an alien astronomer on the other side of the galaxy. Morgan, can you confirm that you can see the Milky Way? Excellent. And I imagine that if they pointed their telescopes to their sun, this is exactly what they would see. They would see our sun's spectrum, and they would be able to use their universal knowledge of spectroscopy that they would get from their own quantum astrochemists like myself, and they'll be able to figure out exactly which molecules and atoms were causing these absorption lines that you see on the screen, and use this information to figure out the composition of the sun. And that's because every atom, every molecule has a unique spectroscopic fingerprint. And if these alien astronomers had just slightly better technology than we have now and were well aligned, they would notice that every year a few new absorption lines would show up in the sun spectrum and then disappear. And then a year later appear again and then disappear. And these would be due to the molecules in our Earth's atmosphere. And they would be able to interpret these new absorption lines and learn a lot about us. You can think of our atmosphere and its subsequent spectrum as a planet-sized message, communicating to the galaxy that we have oceans and forests and varied ecosystems with rich life cycles, and also that we pollute a lot. And we can do the same to them. And that's what I'm working on. It's fascinating to me that sometime in the very near future, questions as ambitious as, does that planet host life, will likely be answered by understanding something as small and fundamental as the quantum behavior of molecules. But this behavior isn't particularly simple. Each molecule has their own spectrum, which look roughly like these ones, describing how each molecule interacts with light. And if we want to detect any of these molecules in astronomical spectra, we need to know what its individual spectrum looks like. And if we want to interpret astronomical spectra correctly and completely, ideally, we want good quality spectra. To start with, we definitely want accurate spectra. So by accurate, I mean we know the correct location and strength of each relevant spectral feature. For example, here in black are my theoretical calculations of the Phosphine spectrum that I did with the exoplanet group in London during my PhD. But mirrored in red are the experimental measurements as provided by the excellent HyTrend database right here at the CfA, who have excellent spectra measured with minuscule uncertainties, and in this case, in agreement with my calculations. So by accurate, I also mean that theoretical simulations agree well with experiment. But good spectra is not just accurate. Spectral quality also depends on coverage. For example, this is hydrogen peroxide, and in blue, you see all of the current experimental measurements for the molecule. The features you see here are very accurate, but that doesn't guarantee coverage in other wavelengths, so that molecule may be spectrally active. As you can see here in red, theoretical calculations also from exomol tell us the hydrogen peroxide actually absorbs a much wider range of wavelengths than the current experimental data would have you believe. And in case you're wondering, this isn't a hydrogen peroxide problem. Hundreds of molecules have only partial spectrum, even really important ones like water. For example, here in red and blue are two different but widely used assumptions of the spectral behavior of water. And they agreed that water was simply not spectrally active beyond about 208 nanometers. In fact, almost every atmospheric model that includes water in this wavelength region is using one of these two prescriptions. The first thing to note here is that these blue lines aren't even measurements. They're just a very reasonable assumption of the water spectrum as it approaches association. But what I want to note is that these aren't necessarily showing the full picture. In fact, my collaborators and I recently found that well beyond 208 nanometers, water's absorption is weak, but it isn't zero. It just hadn't been measured beyond that point. You can see our measurements in pink and purple, and in black, my most conservative theoretical estimate. These new spectral features of water are far too faint to be used to actually detect water directly, but they're not inconsequential. What we found was when these new water spectra were included in photochemical models of planets with abiotic, anoxic atmospheres, so roughly analogous to early Earth or Mars or Venus, the predicted production of OH radicals goes up, and this has drastic consequences for the composition of the atmosphere. Specifically, the predicted abundances of carbon monoxide, oxygen, and in some cases, methane and hydrogen went down by many orders of magnitude. So spectral coverage is really important. A good spectra isn't just accurate and comprehensive, it's also complete. And by completeness, what I mean is that you know how many features of a given molecule you need to correctly simulate it. And sometimes you need loads. For example, here in white, you see the observational spectrum from a methane-rich brown dwarf. Using an experimental spectrum with 350,000 extremely accurately measured features across this whole range, some of the spectrum could be quite well replicated. Some, but not all, despite this many features. In fact, in this case, these data could only be replicated with a much more complete line list for methane, calculated theoretically with 10 billion features, also by exomol. So I've highlighted a few spectral concerns about a few molecules, but as you can imagine, there are many, many more molecules to worry about. And even with this new improved understanding of these molecule spectra, we're only just beginning to understand what it would mean to actually find them in an exoplanet atmosphere. Take, for example, phosphine. When I first started working on phosphine, it was really only known for two things. One, as a marker for violent storms on Jupiter and Saturn. So phosphine is detected in the upper layers of these planets, but it is a tiny bit surprising because the temperature and hydrogen pressure there are far too low for the formation of phosphine to be thermodynamically favored. But what happens is phosphine, after being happily formed in the hellish depths of these planets, it's aggressively dragged to the top by strong currents, surviving to much larger concentrations than that predicted by local thermal equilibrium. But on rocky planets like the Earth, we don't have those extreme environments like the depths of Jupiter. So phosphine is rarely made spontaneously. On Earth, phosphine is mostly notorious for being a lethal and foul-smelling molecule, which brings me to the second thing phosphine is known for. Phosphine interacts fatally with oxygen metabolism, so it's a really effective killer. And for this reason, we often use phosphine as a pesticide on Earth. And sadly, also for this reason, we have used it as a chemical weapon for over 100 years. So phosphine is mostly awful and deadly, but what I found was that it has one very important characteristic. For life that doesn't rely on oxygen, phosphine is perfectly safe. In fact, on Earth, I reviewed all the reports of phosphine detections and found that it's produced on all manners of anoxic ecosystems. So places like sewage, marshlands, or lake sediments, and also the intestinal tract of fish and babies, and actually the guts of most animals. So I wanted to find out, could oxygen-poor planets have detectable phosphine-rich biospheres? To explore this possibility, myself and my team used multiple detectability metrics and photochemical and radiative transfer codes, basically to figure out, A, could phosphine survive in a variety of hypothetical oxygen-poor planets, be detectable in the near future, and be distinguishable from other molecules. And my calculations do show that phosphine has a beautiful and distinctive spectrum, seen here in black, that does set it apart from other molecules, seen here in color. And we found that with JWST, we could detect phosphine on oxygen-poor planets, even around active M dwarfs in both transmission and emission, so with NIRSPEC and MIRI respectively, and with completely reasonable phosphine production rates, so comparable to those found, well below actually, those found above the strongest phosphine producing anaerobic systems on Earth, so places like sewage plants or penguin colonies. Now for sun-like stars, we would find it harder, but still possible to detect phosphine on only a few scenarios, namely hydrogen-rich planets, and only if they really like producing phosphine. So, a sewage planet, an intestine planet. And we did these calculations with JWST in mind, so we could focus on the near future, but lots of other future missions like Ariel, TPFI, Darwin, LUVOIR, the 30-meter class of ground telescopes will certainly be able to characterize atmospheres of planets and wavelengths where phosphine is active. And this makes phosphine really promising as a biosignature. But what makes phosphine really appealing is that it seems to have no significant false positives for life as long as it's found on rocky, temperate planets. So definitely not a sign of life on Jupiter. And to figure this out, we looked first at standard chemical processes, and we found that in all cases, the formation of phosphine was highly thermodynamically disfavored. So then we looked at lightning and volcanism and meteors and found that even in the most favorable atmospheric scenarios, so those that are highly reduced, only a negligible fraction of phosphorus could turn to phosphine, and always many orders of magnitude below anything we could detect. So at that point, we did look into increasingly more implausible scenarios, and none delivered any substantial false positives for phosphine. So with this finding in mind, I wrote this article with a conclusion that read, any detectable amounts of phosphine on a rocky planet cannot be explained without life. And when I first submitted this paper, I thought this was a pretty cool conclusion, but it wasn't controversial at all. It was just me describing a totally theoretical, hypothetical situation no one was really concerned about. I was imagining this sort of distant planet, an anoxic tropical paradise with a rich biosphere producing tremendous amounts of phosphine that we might one day, hopefully when I'm still alive, be able to observe. And you might now know that phosphine turned out to be a little more exciting than I had initially envisaged, because a few months after I submitted this paper, an astronomer at Cardiff called Jane Greaves reached out to me asking for help interpreting a JCMT observation, seen here in white, and later a follow-up with ALMA, shown here in orange, that seemed to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable location on the planet. Jane knew this was strange, but she needed a phosphine expert to know how strange, and that's where I came in and how our collaboration began. Now, the notion that phosphine, a molecule that I had claimed was a very promising biosignature, might be present on Venus is, of course, very exciting. And the press thought so too. But before we jump on life as an explanation, I should point out that there's still very much, well, there's a lot about Venus we don't understand. And all we really know is that there's something weird happening on Venus.
Clara, can I interrupt with a question? So which is the Venus spectrum? A couple people were asking online.
Oh, so both of these are spectra from
the lower panel or the upper?
the lower panel.
It's possible the screen froze. We're seeing the N2 and H2 with different parts per million.
N2 and H2.
Oh,
N2 and H2. Oh, you're seeing a telescope?
No, we're seeing.
I think this is the JWST predictions.
That's right.
Oh, how strange. It must have frozen at that point. Let me stop and start the sharing again. I'm sorry. So you saw this?
Oh, it froze even before that.
We didn't see the
3
telescope.
slides before.
Oh, yeah, I'm sorry. So you were just listening to my voice? God, that must have been tough.
No, I mean, it made sense with what you were talking about, but I didn't realize there was other slides to go along with it. We see the presenter slide again.
That's okay. What about now?
It didn't change for me.
How peculiar. Let's try directly with the desktop. Okay, do you see my presenter notes or the slide?
Presenter notes.
Now the slide?
Yeah.
And now do you see JWST?
We do.
Excellent. Okay, where were you? Okay, JWST, great telescope. We could probably use it to find phosphine, false positives. I was just explaining what you're seeing now. No false positives, yay. Phosphine, great biosignature. This was my imagined planet. And these were the ALMA and JCMT spectra.
Awesome.
Okay,
awesome.
Now it makes sense. Seen here in white and seen here in orange, respectively. So what was that? Oh, yes, I was saying something weird is happening on Venus, but we don't know what it is. And to figure that out, there are many next steps. And specifically, currently, there's a lot of controversy surrounding this discovery. And I'm happy to discuss this here to some extent where I can. But ultimately, what we need to do is address the primary uncertainties of this discovery. Namely, is the signal real? If it is it phosphine? And if it is, what's making it? And to try to answer these questions, I am trying to get more data by looking at Venus in the infrared. And as we learn more about Venus, I'm hoping we can get better models that can actually help us make sense of exactly what is going on Venus. But to make the most of both models and observations, we need better spectroscopic data that can not just describe phosphine, but every other atmospheric component of Venus and how they interact with one another. This spectroscopic toolkit is vital for us to understand what's happening on Venus, and I am working on it, but what I want to highlight here is how a virtually unknown and really quite unusual and disgusting molecule became such an important piece of the puzzle in the search for life beyond Earth. And phosphine is just one molecule and Venus is just one planet. Even if it turns out that indeed we have found phosphine on Venus, this won't be the last time that we find a potential biosignature on a planet beyond ours. So the question is, will we be better prepared to interpret such a discovery next time? And that's where I'm working towards. Take, for example, these slightly more popular and palatable biosignatures. These are molecules that life we find pleasant loves, like methane and carbon dioxide, produced in large quantities by life. But also molecules like hydrogen cyanide, which aren't particularly popular now, but were likely crucial as a building block of life, so a good pre-biosignature. Now we know of these gases and we can and should look for them in exoplanet atmospheres. But none of these molecules on their own would necessarily indicate life, as they all have false positives. And this is true for most of the atmospheric gases that life loves, and it isn't a cruel astrobiological coincidence. This false positive problem happens because the chemical potential energy gradients that life likes to exploit are also easily exploited by geochemical processes. So these molecules are great, I love them, but thermodynamically speaking, they're easy to make. And so detection of these molecules in isolation would never necessarily indicate life. And the main solution to this false positive problem is to carefully consider context. For example, oxygen on its own may not be a good biosignature, but in the exact context of our planet, our sun, and the other components of our atmosphere, oxygen is a wonderful biosignature. And the same is true for most abundant gases we usually consider in the search for life. These molecules are only good biosignatures if they can be attributed to life after an investigation of their false positive scenarios, which requires not just an understanding of the stellar and planetary environment, but crucially, the detection of other, potentially much less abundant atmospheric gases that can provide a chemical context to the discovery. And how many molecules could form this context? Well, my old group at MIT tried to come up with exactly this list of all possible gases that could be produced by life and contribute to an atmospheric spectrum. And that list contains 16,367 molecules. Now, most of these molecules would likely be present in tiny quantities in any atmosphere they find themselves in, but their presence could give us vital clues to interpret their environment and potentially any life within it. So at the very least, we should be able to detect them, but for that, we need their spectra. And sadly, out of those thousands of molecules, we only have a rough idea of a few hundred of them look like, and we only have good spectra for a few dozen of them. And that means we only have spectra of any quality for less than 4% of possible atmospheric gases. For all the other molecules, we have no spectral data at all, which means no hope of remotely detecting them. And you might wonder why that is. Can we just kind of measure them? And we can. We can record these in the lab, but these experiments are expensive. They're often dangerous. They're sometimes altogether impossible. And we would always be restricted by the instrumental limitations of these measurements, as you saw earlier with hydrogen peroxide. The alternative is to simulate these spectra theoretically. And that's what I did for my PhD, but it's also not trivial. I won't go into the details of this here, but the general overview is that to get a molecule spectra, I first study the unique structure and electron distribution of any molecule and use that to solve the Schrödinger equation. First for the motion of the electrons, and then the motion of the nuclei. And that gives me a list of energy levels that a molecule can occupy. But I can also map the distribution and motion of the electrons, also unique for each molecule, and use this to figure out how likely transitions are to occur between pairs of energy levels. This can provide me with isonic coefficients, which can turn into intensities. So now with transition frequencies and strengths, I can simulate the full spectrum for the molecule. But these calculations are really hard. Part of the issue is that for each type of molecular excitation, and there are usually millions of them, solving the Schrödinger equation relies on diagonalizing enormous matrices. And this is a process that to the largest extent cannot be parallelized or interrupted. So to theoretically obtain spectra, it takes years of work per molecule and enormous computing power. Even a small molecule with only 3 or 4 atoms will take at least a couple of million CPU hours, and we usually have to assign each molecule to a graduate student to focus on for the entire duration of their PhD. Take phosphine. We know it pretty well, but that's partially because I spent a large chunk of my 20s simulating its spectrum and associated properties. And I would love to repeat this for all the other molecules, but just one person. And to do phosphine, a single molecule, it took a lot of sweat, a lot of tears, a lot of computer effort, and 4 years of my life. Which means if I was going to tackle those thousands of molecules at the same rate, it would take me well over 60,000 years, which is too long. And I came to this realization a few years ago when I was writing my PhD. Well, it's now 5 years ago. But at the time, I was also the head of education for the Twinkle space mission, a tiny space mission that hasn't even launched. But I founded and I ran EduTwinkle, through which I delivered all the educational programs for the mission. And I was doing this while I was also training as a high school teacher in a London school. I noticed that whenever my research was mentioned in the classroom, the students and I would get into really interesting discussions. So I thought, what if I wasn't working on all those molecules alone? So I created a new program called Orbits, or Original Research by Young Twinkle Students, and recruited 15 of my own kids to research molecules with me and 3 junior scientists who agreed to help. And this is the first cohort of students, which I split into 3 groups, each dedicated to studying the spectra of a molecule crucial for understanding exoplanets and their host stars. So this is Team Titanium Oxide, Team Acetylene, and Team Methane. Now, these amazing kids learned astrophysics, quantum chemistry, programming, scientific writing, and performed original research on these 3 molecules. They went from being my high school students to my scientific collaborators and co-authors on multiple papers. The students you see here then became mentors for next year's students, and those the year after, and so on. I hired someone to replace me when I left the UK, so the programs continue without me. And since 2018, more than 100 school kids have become published authors of scientific papers through the Orbits program. Now, to continue this sort of work, thanks, Anna. In the US, I became the director for the Harvard-MIT Science Research Mentoring Program. In it, myself and a small admin team recruit a few junior scientists, so postdocs and PhD students, and we help them adapt their current astrophysics projects to benefit from student collaborations. I then hire and train and pay a salary to 15 local high school students and assign them to mentors, and they perform original research through the academic year. At the end of the program, we have a symposium, and I'm hoping you'll all attend it this year. And working with these kids has made me feel that it isn't just me anymore. By training and supporting students, we're able to work on obtaining the molecular fingerprint for several new molecules, putting a tiny dent in that list of thousands of potential biosignatures that still need spectra. In the meantime, I calculate that if everyone I've trained joins the effort to obtain these spectra, we could reduce those 60,000 years to a much more reasonable 2 decades, which is encouraging. It just isn't enough. For example, JWST will start providing astronomical data in a couple of years, fingers crossed. And ideally, by then, all of this fundamental spectra should be ready and tested and integrated into atmospheric models. Otherwise, JWST will provide us with incredible data, but from which our insights will be limited. We need these data quickly, but currently measuring or simulating all the necessary spectra on time is an impossible problem, which is why I created RASCAL, or Rapid Approximate Spectral Calculations for All, to simulate approximate spectra for those thousands of molecules using a crafty combination of computational organic and quantum chemistry. The first iteration of RASCAL works by identifying which groups of atoms and bonds, known as functional groups, form active features within a molecule. So for example, every ketone with these atoms has a feature around here, and every alkene with a triple bonded carbon has a feature in this region. And the same applies to literally hundreds of functional groups, which my team and I have spent years collecting and assessing and coding into RASCAL. We wrote some code using chemoinformatics modules that identifies each spectrally active functional group within a molecule, and then I use that to puzzle together a molecule's skeleton spectrum. For example, take dimethyl sulfide. On Earth, it's a volatile produced in large quantities by algae, so quite a cool biosignature already. And RASCAL starts by recognizing that in this dimethyl, the central sulfur atom does nothing for this molecule spectrum. And it's the hydrogen and carbon functional groups that do most of the spectral work. With this information, RASCAL predicts the approximate position and relative intensities of these molecule features, and it does so correctly, as you can see here by comparison with the PNNL spectrum. And more complex molecules, which usually are much harder to do theoretically, are no problem for RASCAL. So here you are looking at the skeleton spectrum for the ethane diamine molecule. And RASCAL identifies the 5 functional groups you see on this table and predicts one strong double feature here with a set of medium features here and a very, very weak feature here. And it does so correctly, as you see with a comparison with NIST measurements. And these are just 2 examples, but RASCAL correctly predicts a comparable skeleton spectra for any molecule I've thrown at it. Here's one final example of RASCAL spectrum. This is glyceraldehyde. It's a molecule present in protoplanetary disks, but it's also the simplest sugar crucial for the energy metabolism of all life on Earth. So a really interesting molecule. And I would love to show you how well RASCAL predicts this complex molecule with all these functional groups, but I can't because there is no infrared spectrum to compare it to, despite this being an incredibly important molecule. But I can, in the meantime, at least provide some approximate spectral data for glyceraldehyde and by extension for thousands of other molecules. And it only takes me a few seconds. So it may not be the most accurate spectrum yet, but it is very quick. If you compare it to my Phosphine spectrum, which took 4 years, you're looking at a process that's 63 million times faster. So RASCAL does all this by predicting the main spectral features of over 16,000 molecules, which is more molecules than any public database in existence. So it's worse data and it's less data, but it is more molecules. Quantity versus quality. So for hundreds of molecules for which there is experimental data for comparison, and by extension for thousands of molecules for which there is no other data source, RASCAL can correctly approximate infrared spectra. And this is the preliminary version of RASCAL. Even at this early stage, it can still be very useful. Anna, I was going to go through some of the applications and future work, but perhaps we don't have time. I don't want to go over. Could you let me know with all the interruptions? You sure?
Go ahead.
Okay. I don't like going over. Okay, so I won't go through the applications of Rascal. Also, there are many, but I'll highlight kind of my favorites that may be useful for people who are here. So you can look for lots of patterns by filtering by functional group and molecule type. But one of the cool things you can do is ask Rascal, what are good molecular candidates for explaining particular atmospheric features in your data? If you have a mystery bump, I can tell you what molecules could cause it. But what I want to focus on is that Rascal can tell you which molecular detections that you would like to make are vulnerable to misassignments and degeneracies. I'll give you one example. So take hydrogen cyanide, one of the pre-biosignatures I mentioned earlier. Its infrared spectrum can be completely explained by this one functional group alone. Through its bending, motions, and stretching motion, it forms the three main features of the hydrogen cyanide infrared spectrum, which means by seeing these features, maybe you did detect hydrogen cyanide, but every other molecule with this functional group will have similar features. For example, acetylene has the same functional within it, and as such, they have similar spectra and they're hard to tell apart. And this isn't just an issue of distinguishing between the two. Rascal can tell us that no less than 890 molecules have the same functional group. And so it'll be really hard to tell apart. The trick that Rascal can help you with is by considering other functional groups within the molecules. For example, the most spectrally active functional group for propene and 1-butene is the same as acetylene and hydrogen cyanide. But Rascal can tell you that they have other features that can help you distinguish them from molecules with the same functional group. So it's really important to note that sometimes the molecule's strongest feature is not that molecule's most distinguishing feature. And any detection that doesn't take that into consideration will be vulnerable to mistakes. So Rascal is great because it produces approximate spectra for any arbitrary molecule, but it has all sorts of other useful applications that are only possible with a large database. And that's Rascal 1. For Rascal 2, which I'm working on here at the CfA, I am making many improvements. First, expanding from the infrared into the optical, UV, and submillimeters where possible. But I'm also estimating band shapes by using quantum chemistry approximations to add flesh to the Rascal skeleton spectra so it can be used as cross-sections for input into atmospheric models. I'm also expanding Rascal from the gas phase into liquid and solid spectra so that, for example, we can characterize ices on Pluto and icy moons. This is actually work I began many years ago when I was a master's student. And finally, I'm harvesting absolute intensities from lab data where it exists and from standard machine learning quantum simulations, such as these that you see on the screen, where I can do them quickly. I've already begun some of this work with a student-led collaboration at the University of New South Wales. And for the molecules we care about the most, we can do it the hard way, like I did it for phosphine. I just won't be able to do this for all the molecules, nowhere anywhere near all the molecules, which is why Rascal is so important. Given how difficult it is to obtain high quality data for those thousands of molecules, thousands of potential atmospheric gases, it is crucial that we invest in intermediate approximate steps to obtaining spectra that can be gradually improved upon, so that one day we can do more than just tentatively detect a promising biosignature like phosphine. Because as much as I like phosphine, which I do, and I also like the more traditional biosignatures such as oxygen and methane, I don't think the detection of life will come from a single molecule. As the Venus story shows, the detection of life will likely be uncertain, and that uncertainty will only be reduced if we are willing to both detect and understand more molecules, even if they're not popular or abundant. Because it may be harder to detect a trace gas that has small impact on an atmosphere spectrum, but if we want to reduce our chances of false positives and consequently increase our chances of actually confirming life, we have to be willing to consider the big picture, not just a few promising molecules, but all possible molecules that can together help us reduce the ambiguity in the detection of life. But today, we are not prepared to both detect and confirm the presence of most molecules on an exoplanet. So my biggest professional concern is not that we'll fail to detect a habitable planet in our lifetime, and even an inhabited planet in our lifetime. My biggest professional concern is that we'll point our telescopes directly at an inhabited planet and not have the tools to know it. So with computational chemistry and collaborations with scientists of all ages, I aim to provide the spectroscopic toolkit that will allow us to, one day, know life when we see it. Thank you.
Thank you so much. So I want to start a conversation by just reminding everyone that they can private message me and I will call on you to speak up. But I wondered if we could talk a little bit for someone who's not a spectroscopist. Something that you touched on in a couple of places is kind of the distinction between features and the incredible number of features that can populate a molecular spectrum, even if we're talking about like a pure molecular spectrum of just one gas. And then I imagine that, you know, if we think about like Earth's biosphere, there's even more than one like biomarker present. So like it must be even more messy. So can you talk a little bit about how in a low resolution spectrum, like we would be able, or a comparatively low resolution spectrum, like we would be able to take of an astronomical source, do those lines add together in a way that it's sort of their like cumulative equivalent width within some wavelength range versus like having single features? So, and I'm coming at this a little bit from, you know, in supernovae, people talk a lot about iron line blanketing. So that's a context that I'm personally a little bit more familiar with, but I wondered if we could kind of start there with what is it that we are really observing? Are we observing individual features? If we were to observe this in 2 decades with an exoplanet or with JWST, or are we observing their like cumulative effect?
So yes, atomic spectra is it's very hard in many ways, but it's a little easier in many ways because you're looking at single lines. With molecular spectra, as you can imagine, there's more complexity, and with that come more lines. In the microwave, we're still able to sometimes be able to isolate individual lines. And that was what we were trying to do on Venus with phosphine, a single transition. I point out of those 16.8 billion transitions that I worked on. So just the one that we were trying to find on Venus. So there are times where you can try to identify single transitions, but yes, most of the time you're looking at bands. So a combined opacity from often millions and millions of features. Mm-hmm. It still varies a lot between wavelengths. So say in the infrared, it's very common for many atom molecules to have features that are quite distinctive. And then as you move towards the optical and the UV, where there are many, many energy levels that can be occupied, but each are not very likely to be occupied, the result is we call them weeds, because instead of getting flat baselines with sharp features, you just get these undulating rolling hills of spectra where it's so hard to distinguish one molecule from another. Mm-hmm. And this is just talking about individual molecules. If we're looking at an atmosphere, it's not a bunch of molecules going about their business unaware of their neighbors. They're colliding with one another, exchanging energy with one another, which not just broadens the features, it shifts the features. It's chaos. And when I say we're missing spectra from most molecules, that's just the pure spectra. Right. We are even worse at figuring out what that spectra would look like when the molecules are colliding with one another, which sadly is literally every time we found them on atmospheres. You never just get, isolated phosphine atoms, molecules. So in answer to your question, it varies, and it depends not just on resolution, but kind of localized context of what's happening to those molecules, what temperature, what pressure. Is the pressure caused by things like CO2, a very successful collisional molecule that just exchanges energy and ruins all the molecule spectrum, which, by the way, is a problem on Venus, which is basically all carbon dioxide. So yes, it is much more complicated than that, and often you cannot go for single features, but that's a problem on top of my current problems, which, as you can tell, are many and would last me lifetimes to resolve all on their own.
Yeah, and I didn't ask from a point of like pessimism or pure pessimism. It seems like some of the work that you're doing to like add sort of like line widths or like cumulative line widths to the groups in Rascal 2 ticks is like addressing some of what I was asking about, though. In a way.
Yes. Yeah, so Rascal will be less crap very soon, but it will still be very much, incapable of doing a lot of the very complicated modeling that we'll need to really understand, you know, a biosphere holistically, for lack of better words.
Yes, that makes sense. Towards a holistic atmosphere, Avi, you had a question about Venus. Would you like to go ahead?
Oh, sure. So, I mean, there was the report in the New York Times, but if we look at the archive, there was some criticism, well, first about the statistical significance of the detection of phosphines, and then some other people suggest maybe SO2 is confused with the line, and perhaps there is volcanic activity that can produce it. Can you comment about these various criticisms and just explain why you believe that it's a real detection?
Oh, I don't believe it any more than I think any responsible scientist does. The team that I'm part of, and I'm not involved in the data reduction, so I'm kind of just trusting the experts. They still think the signal is real, and other teams think so too, but not all. So there are ways of reducing the data where the signal disappears. So maybe the signal is not real. But even if the signal is real, indeed, when we were looking for candidates to explain the signal, phosphine was our favorite, but our second favorite was SO2. Now, SO2 was dismissed for a variety of reasons. The kind of the easiest one to explain is that in the bandpass, there were other locations where SO2 should be absorbing. And so we looked there and there was no SO2. So it can't just disappear easily, though there are ways of having enormous variability. And so we ended up dismissing SO2 for various reasons, including this one. But SO2 would also be a strange thing to find where we found it. The distribution of SO2 between kind of above the clouds, within the clouds, and beneath the clouds are things we still don't understand. Now, when I say it would be weird to find it, it's not as weird as finding phosphine. So obviously something worth exploring. But these are all things we considered. I should point out that there's a lot of kind of criticism of lots of work and infighting and things like this. But this is just a bunch of very good, very well-meaning people trying to interpret very difficult, very noisy, very delicate data. And discoveries made at the edge of instrument capabilities will always lead to discussion, as they should. Because if we could just look at Venus and go, yay, phosphine, aliens, we would have done it. And it's really hard. So I'm not involved in the data reduction. I don't really want to be defending something I don't understand completely, but that's kind of the general summary. It seems like these are huge disagreements, but they're not. It's things like, oh, the upper limit of phosphine has to be 5 parts per billion. And we go, I think there's 7. And this seems like a huge disagreement because it's basically someone saying we found phosphine and someone saying we didn't. When actually it's a 2 part per billion difference, potentially. So
did you feel that some of the criticism was unfair and mean-spirited, or did you feel that it's collegial?
Some was perhaps a little clumsy, I would say, but I think it's mostly collegiate and well-meaning. And this is exactly the sort of discussion that I would have been disappointed if it was absent. If we had claimed a detection of a potential biosignature next door and everyone went, great work, let's move on, that would have been a horrific disappointment. And so I'm really pleased that it has led to this debate, because this isn't our last time. I feel like this is our rehearsal for next time we find a biosignature, and I want to do better next time, by which I mean be better prepared with a better toolkit, with more transitions. I've always been against, as you've seen from my talk, detecting a molecule with a single feature, because obviously it's very easy to make mistakes. And with Venus, we would have loved to have additional features so we could confirm it's phosphine. And that's very much where my efforts are at, following up with Venus to try and get more features. But no, I definitely don't think people are mean-spirited. Everyone's just trying their best. And also it's a pandemic. We can all go easy on each other.
That's a good, lesson for life right now.
Let's
Anna,
be nice.
Would you like to go ahead with some discussion about like the stellar type and how that relates to detecting?
Yes, I remember especially you mentioned for phosphine. By the way, really nice talk, thank you.
Nice.
Yeah, and so the question is, you mentioned that phosphine is more difficult to detect in solar type than M-type stars, and then you started talking about different kind of molecules. I was wondering if, well, first, like why that is for in case of phosphine, and then second, like does this apply to other biosignatures as well, and could this kind of potentially lead to kind of a bias of what kind of life we can detect, because you're saying that like those other biosignatures are not unique. So if you need like a combination of those, but you can only detect certain molecules in certain type of stars. So anyway, that's what I was wondering.
No, totally fair question. So this is a complicated game with many parameters. In the case of the stellar type, it kind of does affect almost all biosignatures, because you can consider, so I'll be really simplistic. If there are any stellar astronomers here, please forgive me. But you can kind of think of, quiet M dwarfs and then active M dwarfs and sun-like stars in kind of growing degrees of radiation levels. And what they do is cause photo dissociation of the molecules. So this photolysis that can destroy molecules, namely biosignatures, gets worse as you move down these stellar types. So when I first did my models, I actually did quiet M dwarfs, and phosphine could totally survive and all these other biosignatures. And then someone said, there's no quiet M dwarfs, so that seems a little disingenuous. And I was like, you're right. Maybe we haven't found them, but I just took that out because yes, you could detect biosignatures, but probably those stars don't exist. So maybe not a good target. But indeed, with active M dwarfs, phosphine struggled much more to survive, and many other molecules, biosignatures did, because by the time they get to observable layers of the atmosphere, they get destroyed. Now, there are ways of avoiding this with protection. So some molecules can work as scavengers, as protectors of the other biosignatures. And these vary depending on stellar type, planetary type, and atmospheric composition. You can also get hazes. They're very good at protecting biosignatures, but then we can't see through them, like with Venus. So the sort of environments that maybe create a protective layer and allow for biosignatures to occur often also shield them from being visible to us. If we can see it, maybe radiation can also get through and destroy them. So this becomes a delicate game with small windows of opportunity, spectrally speaking, where we can see these biosignatures, and it varies enormously on super Earths versus smaller planets, planets that have hydrogen-rich atmospheres versus nitrogen-rich atmospheres. And so this combination, this complicated game has a very large parameter space, and playing around in those and figuring out what are our windows of observation, that's kind of what I'm trying to do.
That's super interesting. And like the work with Rascal, that when you're mapping all of those kind of spectra individually, like do they sort of add up in this game of like scavenger molecules? Like, so does this provide you the tools to kind of simulate such environment as well?
Very roughly. So they just, if I know it's a methane-rich atmosphere, and that's one of the things Rascal can do, it can tell you what are the windows already, because I already know that, and tell you which molecules are good for being detected in those windows. And it can also tell you which molecules only have one feature in those windows, meaning detecting it unambiguously will be very difficult, as we just saw with Venus, and which have two or more, meaning you could play a game of unambiguously assigning it. So very difficult, but possible. And I'm kind of just trying to do the first very clumsy step into exactly that toolkit.
That's pretty cool. Thanks.
It is really interesting. We just have another question. Martin, would you like to speak up about M dwarfs?
Oh yeah, I just saw that. I can read the message. So the question is, if it does struggle on active M dwarfs, it is a good biomarker because it must be produced continuously to be detectable. If you know the half-time, you can use it. Sorry, no microphone here.
Oh, yes, I didn't see that part. Yeah, thanks.
And yes, so absolutely. But it is a bit of a game, right? You want it to have a short enough half-life, lifetime, that if you see it, you know it's a good biosignature, at least to some extent, because it has to be continuously produced. But if it's being destroyed too quickly to accumulate to detectable levels, then you just won't see it at all. So you also have a very small window where it's a good biosignature with low false positives, but you can see it. And this dance is not straightforward. So yes, but that comes with downsides.
Interesting. Gary, go ahead.
I have a quick question about JWST. Do you know whether JWST will have the ability to detect some of these biomarkers? And in particular, it's my understanding that you need to integrate for a long time to detect some of these spectral features. And JWST was not built to integrate down the noise for the length of time needed to detect these species. So I'm wondering if you've looked at these issues and you've isolated a set of potential targets that are suitable for JWST's capabilities.
So excellent question. And this is something we looked into a lot. So one of the planet scenarios I didn't mention was CO2-rich atmospheres around sun-like stars, where technically I found that JWST could detect them, but it would have to use its entire cryogenic lifetime to get a good enough signal-to-noise ratio. So I didn't mention this and didn't add it to the paper because that would be really disingenuous. And
that should be no problem for all of your colleagues.
But that was exactly something we took into consideration, kind of how many observation hours would it take? In our most favorable scenarios, we only need a few tens of observation hours to be able to get a really robust signal to noise ratio. But in others, it would take hundreds. And I've kind of mentioned this in the paper, but I'm not really an observer. I only proposed for like 2 observations in my whole life, and they were both for Venus and both in the last year. So I'm very new to that field, but we definitely took that into account. And it was, for someone who's coming from a different field, really heartbreaking, because we would run these simulations and be like, oh, we could totally look at that spectrum, we could totally see phosphine. And then I figure out how many hours of JWST observation we would need. And it's just, 208. And I just gave up on that. So yes, definitely a consideration. I haven't got to the point where I have simulated all the possible scenarios with all the possible molecules to try and figure out what JWST can and cannot do and what are the best targets. But if anyone here has kind of the chops to do that, I would love to collaborate, because observing is very much new to me. I'm a theoretician and not even a theoretician in astronomy. So this is
let me just mention a cautionary note. For an instrument like those on JWST, they're built to attain a certain stability. And what that means is that even at their listed sensitivity, you could integrate for 10,000 hours and your signal to noise will plateau. It will not continue to go down as the square root of time, because there's an inherent instability, an inherent noise in the instrument. So as you look at this with JWST, I would just caution you that it's more than just looking at sensitivity and assuming radiometric performance of the instrument. There will be a noise floor you can't go below. So just a note that even at 200 hours or 100 hours of integration, JWST may not be able to do what you want.
Yes, quite possibly. I'm very willing to believe that I have to chop everything in half or double all the observation times and plateaus are hit. These were the codes we use that include noise floor, and so I'm thinking the most favorable scenarios may be possible, but that's really as far as I'm willing to promise. And we only use JWST because that's kind of near future and we have access to some simulations that allow us to do, but this sort of work is likely only going to be truly useful for the kind of the next generation of telescopes.
So let's go back to the lab.
Yeah, in the meantime, yeah, we need more spectra anyway, because we can't see most of the molecules. So someone has a question. Phil. Yeah.
Yeah, sorry. So fantastic talk. Thank you very much. So coming from a stellar spectroscopist point of view, one of the main hurdles there is reconciling the difference between the laboratory measurements of oscillator strengths of iron, for instance, and the predictions, quantum mechanical predictions. How well are we doing with these molecules? Are the quantum mechanics in agreement with the labs, or are like the wavelengths are way off, or the oscillator strengths way off, or anything like that?
So kind of the short answer is, if you can have experimental measurements in that region, you should use those. It would be kind of my shorter answer. So if it's in Haitran in that region, take it. But the problem is there may be other regions where it's active and there's just no data. So you need to make some choices. And the kind of the easiest explanation I can give is you should always trust the positions of measurements, and you could probably do well with trusting the intensity of the simulations. Because when you're measuring, it's often very difficult to get the baseline clean enough to know the true intensity. And it's very hard to know how much that varies with temperature from one measurement at a single temperature. And so intensities tend to be a little better with theory, and positions tend to be better with measurements. Now with big molecules, simulations, high performance computing simulations, they tend to get really bad really quickly as soon as you get to like 5 atoms. And that's where Rascal is trying to step in, because Rascal doesn't care how big a molecule is. But the matrices just get completely undiagonalizable once you get to high excitations. And with big molecules, there's lots of things to do. So it varies, but yes, measurements tend to be better at frequencies, theory tends to be better at intensities, but both benefit from one another. And so often people imagine that we're competing with one another, and I'm not gonna lie, sometimes there's some, rough words spoken in conferences, but mostly we need each other very much. All of my work would have been impossible to refine the theory without reliable experiments that I could trust and benchmark against mine. So we kind of need them both, but yes, they have their strengths and downsides.
Thank you.
So can I guess, pose a little bit of a question, but also just give you this last minute or two to sort of have the last word. Something sort of that came up to me again and again through what you showed is that if we have approximate identifiers of molecules, we can kind of take a learning approach of like, maybe we see certain lines in a spectrum. Maybe it's a solar system spectrum, maybe it's extrasolar. And then you, with your line identifications from sort of an approximate code like Rascal, can tell us what like candidate molecules are. And then you could follow those up with more in-depth sort of study. Do you think there's a prospect for essentially empirically using the astronomical spectra to learn more about the full spectrum of a molecule, like one of these complex molecules that's hard to compute? Or is the lab always going to be our point of reference?
No, we've used astronomical spectra to calibrate things. Yes, particularly at high temperatures. You can get spectra from cool stars, which aren't that cool, but cool enough to have quite a lot of molecules, and we can identify the molecules by famous bands and things like that, and then see how they vary with the very high temperatures. We wouldn't be able to simulate in the lab. We're not going to simulate those sorts of temperatures easily and safely for all the molecules we care about. So yes, we have in the past used astronomical spectra to calibrate pure spectra that we have from the lab and from theory. So yeah, maybe it's a tripod, astronomical spectra, lab spectra, theoretical spectra, ideally working together and iteratively. I mean, not the solar spectra, they don't care what we do, but but using all of this data iteratively to improve one another, definitely something that is done. I should point out on a less positive note that these fields don't necessarily communicate with each other particularly well. So there's a lot of information lost along the way. Oh, and I get the last word. Yeah. If any of you are interested in being mentors for my outreach program and you don't completely hate children, you should join. We always need more mentors, and we also need funding because we can't pay the mentors, but we do pay the kids. I get money to pay the kids. The kids get paid.
That's really wonderful. Well, thank you, everyone. Thank you, Clara. We're delighted to have you at the CfA to the maximum extent that's possible. And thanks for sharing this hour together.
Thank you for having me.